Alright, here comes the solution of this rather simple problem, but it was only meant to be a warm-up of the next problem. And I will post the next problem, which is really an extension of this problem, at the same day that I post the solution. So let's look over the problem again. This was a planet which has no atmosphere. It has a mass, capital M, which is given here. It has a radius, capital R, which is given here. And we launch an object in the vertical direction. I stand here and I launch it in the vertical direction with speed v, and it has a mass 137 kilograms. It slows down, it slows down, it slows down, and it comes to a halt at that point 2, and the distance from the center of the planet to that point 2 is 3 radii. And then of course when it comes to a halt, it falls radially back to the Earth, and it's not the Earth, it's a magic planet. And then it will hit the planet with that same speed v. And the question is, what is that speed v? Clearly, energy is conserved. There's no atmosphere, there's no air drag. So the change in potential energy between these 2 points is converted to kinetic energy. So the potential energy at point 2 minus the potential energy at point 1 must be 1/2 mv squared, m being 130 kilograms. The only sane way in situations like this to deal with potential energy when you are large distances from a planet is to define the potential energy 0 at infinity. That means at all other distances from the center of the planet, the potential energies will then be negative. There's nothing wrong with that. Even though it's negative here and it is negative there, the potential energy here is still larger than there. And it is that amount by which is larger, potential energy 2 minus potential energy 1, that gives you the 1/2 mv squared. So, the potential energy at this point is minus m capital Mg over 3r, this distance is 3r, and right here it is minus mmg over capital R. But since there's a minus sign here, this becomes a plus sign, and that is 1/2 mv squared. And so v squared is 4/3 mg over r, and that gives you a speed here of 9.128 kilometers per second. Very reasonable value. Perhaps many of you recall what the escape velocity is from the Earth if we ignore the atmosphere of the Earth. And in this case there is no atmosphere, very special planet. And so I remember from my high school days that the escape velocity from Earth is about 11 kilometers per second. I don't remember it to any better accuracy. But here I want a higher degree of accuracy. You will see why, because it has to do with the next problem. So here I prefer 4-digit precision. 3 is allowed, 2 is not allowed. So if now I calculate what the escape velocity is, then of course point 2 is at infinity. So it goes from 1 all the way to infinity, and it comes to a halt at infinity. So this term is 0. So PE 1 is negative. But at infinity it is 0. And so the energy that is released is this amount. Because this minus mmg over r is the potential energy here. But it is PE2 minus PE1, so that makes it a plus sign. This is gone, So for escape velocity, v squared is 2 mg over r. And that gives you 11.18 kilometers per second. Consistent with my high school memory, 11 kilometers per second. Okay, so now get ready to do the next problem, which will be online within 1 hour of my posting this one. And if you cannot do this one, there's no hope that you can do the next one. Sorry for being so negative, but it's okay if you cannot do the next one. It's also okay if you cannot do this one. If you cannot do this one, you may want to watch my lecture, my A21 lecture, in which I discuss potential energy at distances far away from Earth. Near Earth, you can always define the potential energy at mgh, as long as this little g doesn't change. So if you lift up an object from the floor to the first floor, g is 9.8 meters per second square on the floor and on the first floor. So that's okay, but you cannot do that if you're so far away from the Earth that g is no longer 9.8. And that's what we take into account when we define potential energy at infinity zero. And I discussed that in great detail in one of my A21 lectures. So you may want to revisit that one. Okay, ready for the next problem? I am.